All right. This is Advent of Code, day 23 in 3, 2, 1, go. All right, unstable diffusion. You enter a large crater of gray dirt where the grove is supposed to be. All around you, plants you imagine were expected to be full of fruit are instead withered and broken. A large group of elves is formed in the middle of the grove. This volcano has been dormant for months. Without ash, the fruit can't grow. You look up, see a massive snow-capped mountain towering above you. It's not like there are other active volcanoes here. We've looked everywhere, but our scanners show active magma flow. Clearly, it's going somewhere. They finally notice you at the edge of the grove, your pack almost overflowing from the random star fruit you've been collecting. Behind you, elephants, monkeys explore the grove, looking concerned. Then elves recognize the ash cloud slowly spreading above your recent detour. Do you just... Before any of them can inform a complete question, another elf speaks up. Okay, a new plan. We almost have enough fruit already, and ash from the plume should spread here eventually. If we quickly plant new seedlings now, we can still make it to the extraction point, spread out, reach into the pack and pull out a tiny plant. Rely on important nutrients from the ash so they can't be planted too close. There isn't enough time to let the elves figure out where to plant the seedlings themselves. You quickly scan the grove and note their positions. The scan shows elves, an empty ground dot. Outside your scan, more empty ground extends a long way in every direction. The scan is oriented so that north is up. Orthogonal directions are written N, S, W, and E, while diagonal directions are N, E. Okay, whatever. Elves follow a time-consuming process to figure out where they should go. You can speed up this process considerably. It consists of some number of rounds during which elves alternate between considering where to move and actually moving. During the first half of each round, each elf considers the 8 positions adjacent to themselves. If no elves are in one of those 8 positions, the elf does not do anything during the round. Otherwise, the elf looks in each of the 4 directions in the following order and proposes moving 1 step in the first valid direction. If there is no elf in the north, south, east, it moves north. Okay. Okay, so they move in a certain direction, and then got it. Only elf moving in that position. None of those elves move. Okay, so if it's the only elf to propose moving to that position, they move. If 2 other elves propose moving to the same position, none of those elves move. At the end of the direction, the first direction the elves considered is moved to the end of the list of directions. During the second round, the elves propose moving to the south first, then the west, then the east, then the north. Okay. Got it. How many empty ground tiles does that rectangle contain? Okay. Puzzle input. Woo-wee. Okay. Wow. Point t equals x int y int fields and let create xy equals xy. Elves print s sex list.take elves 10 point.t list. map I line string dot to list line list dot map I so this is Y map I fun X iter let else equals hash set dot create module point in if ch equals then hash set dot add point dot create xy elves ref elves 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 do let n equals equals -1 x -1 let east equals, let's do it this way, equals 1 -1 let east equals 1 0 let southeast equals 1 1 let south equals 0 1 southwest equals -1 1 let west equals -1 0 let northwest equals -1 -1 let all ders equals n e e s e s s w w n w let norths equals northwest north northeast let easts equals northeast east southeast let souths equals southeast south southwest let wests equals southwest west northwest. north, south, west, east. Let dir checks equals norths, souths, wests, easts. Okay. Let run round equals current locations equals dir checks equals in. So we have to for each elf generate proposal check all around, check each dir check. Pick first one that works. Then check each proposal, check if any conflicts. Okay. But I don't know why I was making this a okay. Elves. Let elves and oh. How do I want to do this? But I do want this to be a hash set. Hash set dot create module point. Hash set dot add set dot to list. Okay. Elves. Let proposals proposed by oh my god, why am I making this complicated? I'm like thinking about performance. Okay. Elves and let proposals equals hash table dot create module point. in let proposal counts equals hash table dot create module point in let anchor counts point equals hash table dot change counts point function none 1 sum c plus 1 anchor counts anchor count. Okay, yeah. Hash set dot iter elves f elf let proposal equals propose move elf elves dir checks in the northernmost elves Okay, I assume that choosing to not move also counts as a proposal to move. Oh, but if they propose to move, they only propose to move if there's not currently an elf there. Okay. Let propose move elves dir checks equals let all surrounding empty equals all dirs dot for list dot for all alders fun dx dy let point dot x y y equal elf in hash set not hash set dot mem elves point dot create x plus dx y plus dy in if all surrounding empty then none else let proposal equals dir list dot find dir checks fun checks what all empty deltas equals for all deltas in all empty all dirs. If all empty checks, then all empty. Option dot map first list dot head exon. Dot map option dot map fun dx dy point dot create x plus dx y plus dy. Promote move match with none, don't do anything, some proposal hash table dot create or add exon proposals key elf data proposal anchor count proposal counts proposal. And then hash set iter elves again. Oops. Now I want to do hash set dot map. Is there a hash set dot map? No. How is there not a map? That's weird. Do I have to list? Okay. To list. List dot list dot map hash set dot of list module point. And so we want to do if match hash table dot find proposals elf with none, then elf some proposal if hash table dot find xn proposal counts proposal equals 1, then proposal else elf. Then we want to do for equals 1 to 10 do let dir checks equals ref dir checks in run ref elves run round elves dir checks equals let head equals list dot head xn dir checks in list dot tail xn dir checks head. Let x equals 1 to 4. Let head equals list dot head x and x. Let, and then we want to do list dot tail x and x head. What? Oh. How can I add to end? Oh, I can do list dot concat this.concat this.tail x and x head. Okay. And then let's just print f there are elves. Hash set dot length elves. Let points equals hash set dot to list elves in let x's equals list dot map points point dot x in let min x width equals list max x's minus list min x's plus 1 in x width times y height. Sum 1. Oh my God. $68.06. Nope, too high. Okay. $132. Oh, minus hash set dot length elves. $110. Okay. $68.06 minus 27.15 40.91. Oh, 7 seconds to wait. All right, there we go. Part 2. First round where no elf moves. Let any moved equals ref false in then any moved equals true any moved. Let round count equals 0. let any moved equals ref true in while any moved do. Else let new elves moved. Oh. New elves anchor round count. Any moved equals moved. Print part 2 round count. Let originator checks equals let new elves equal new elves $10.36. Let's go. Oh, oops. Okay. All right, we did day 23. So how did we do it? This one's pretty straightforward. We have a bunch of positions, and basically all of the pound signs are an elf, and they move according to certain rules. So I have a point, and then I have this thing to parse to get a set of all of the elf positions. And what I do, they check the spaces around them. So I hard code all of the deltas, keeping in mind like north is negative because y's are going up, going down, so it's reversed. Each elf checks all of the spaces around them. If they're all empty, it doesn't do anything. Then it checks the spaces in a certain direction in a group. And then if all of those are free, it'll move in that group. I get all of the elves. The dir checks are these are all of the directions, and then I have each of these, like all of the north directions, the south directions, have those in an array. And so part one, we are supposed to run 10 rounds. So we run the round, passing in the elves and the dir checks. So we run around, we create a hash table from points to where we're proposing we move things. And we're also keeping track of how many elves are proposing to move to a location. And we also keep track if anyone actually moved. So we iterate over all the elves. We propose a move. We try to propose a move. If we don't get anything, we don't do anything. If we get a proposal, then we add that to our hash table of proposals. Oh, I don't even need this. Oh, yes, I do. Add that to my hash table of proposals, and then I increment the count of how many times, how many elves want to move to that location. Then I recalculate the elf positions by looping over all the elves. If there's no proposal for that elf, it stays put. If there is a proposal and the count is only one elf wants to move there, then the elf moves to the proposed place. Otherwise, they stay put. And we also say that, okay, there was an elf that moved, and we return that. Then the other wrinkle is that this, like the directions that they check, north, south, west, east, each round, these like cycle. So the first round, they check north first, then the second round, they check south first. And so that's what this little thing is. And then for part one, we run 10 rounds, get the bounding box, and count how many empty spots there are in the bounding box after 10 rounds. How many empty spots, subtracting out the number of elves themselves. So it's pretty simple. Get the points, get the x and the y's, max minus min plus 1, and then multiply them minus the number of elves. Then for part two, we just want to see how many rounds it takes. So I just copied this and then keep track of the rounds and then break when nobody moved. Yeah, so that is Advent of Code day 23 in OCaml.